In this example problem, we're going to find the sustained live load and total stress and strain conditions corresponding to the given loads for the T-section that's shown. Because we're looking at sustained loads, we have some information on creep and shrinkage, so our creep coefficient and our shrinkage strain. These are given here, but if they weren't given, you could find them using any procedures for a creep or shrinkage. So ACI or AASHTO procedures. So the first step is we're going to find our gross section properties. And we need to find them here because they're not given. Gross section properties are often given for pre-stressed precast sections. And if you are given the gross section properties, you can just use the given properties. You don't need to calculate them yourself. So anyway, we'll start with our gross area. So we have 12 inches times 16 inches plus 20 inches times 8 inches gives us an area of 352 square inches. And note that I'm breaking this into two rectangles. So we have a 12 by 16 rectangle there, and then we have another rectangle here, 8 by 20. So that's what I'm adding. So next we can find our YT. So we're going to use the area times the distance from the top to the centroid of each section. So we're looking at the distance from the top to the centroid of each of these sections times the area, and we'll divide by our total area. So here we'll have 8 inches times 20 inches times 4 inches, which again is the distance between the top and the centroid of that top rectangle. So our area 1. And then we add in 16 times 12 times the distance from the top to the centroid of that area. So 8 inches plus half of 16 is going to be 16 inches. And we'll divide by our gross area, 352 square inches. So this will give us a YT equal to 10.5 inches. And that's the distance between the centroid of our section and the top of the section. Next, we can find our gross area, and we're going to use parallel axis theorem here. So we'll take the I of each of our components 1 and 2 and add in our AD squared component. So we'll have our I gross equal to 20 inches times 8 to the third divided by 12 plus 20 inches times 8 inches. So our area times our D, 10.5 minus 4 squared. And then we have our I and AD squared component for our second rectangle. So 12 times 16 to the third divided by 12 plus 12 times 16. Our area times our D squared component, 10.5 minus 16 squared. And this will give us a gross moment of inertia of 17,517 inches to the fourth. Our next step is to find our material properties and our modular ratios. And we'll need to find both our short-term and long-term modular ratios because we're looking at both short-term and sustained load effects. So we can first find the modulus for our concrete using our F prime C. So 6,000 psi in there, and we can find our modulus to be 4,415 ksi. We can find our effective modulus. So this is taking into account the effects of creep by taking our modulus, 4,415 ksi, divided by 1 plus our creep coefficient, 1.8, which was given. And we'll get our effective modulus to be 1,577 KSI. Next, we can use our modulus for our pre-stressing and our modulus for our concrete to find our short-term modular ratio. So we have 28,500 KSI divided by 4,415 KSI will give us a modular ratio of 6.46. The effective modulus for our pre-stressing, taking into account the effects of strand relaxation, was given here as 27,930. And we divide this by our effective modulus for our concrete, taking into account the effects of creep. And we'll get a modular ratio of 17.71. We can then use these modular ratios to transform our pre-stressing into an equivalent area of concrete. And we can calculate our short-term and long-term transformed area. So our short-term transformed area is going to be our gross area, which we found on the previous slide, 352 square inches, plus 6.46 minus 1 times the area of our pre-stressing, 0.651 square inches. And this will give us a transformed area here of 355.6 square inches. Our long-term transformed area is going to be 352 square inches plus 17.71 minus 1 times 0.651 square inches will give us a long-term transformed area of 362.9 square inches. Now we can find the distance between the top of the section and the centroid of our short-term and long-term transformed section. So we'll start with our short-term. So our first area is our gross area, 352 square inches, times the distance between the top and the centroid of the section, which we found before is 10.5 inches. Then we add in 6.46 minus 1 times our pre-stressed area, 0.651, times the distance between the top and the centroid of our pre-stressing, which is going to be 20 inches. We'll divide all this by our transformed area, 355.6 square inches, and this will give us a transformed centroid of 10.6 inches. So we can check this conceptually to make sure that we have our calculations correct. The distance from the top to the centroid of our gross section is 10.5 inches. So this area of pre-stressing is going to pull down that centroid. So our centroid here, this 10.6 should be greater than 10.5. So it is, so conceptually it makes sense. We can do the same thing with our long-term modular ratio. We're just switching out that value there. And we can find a distance between the top and the centroid of our transform section, taking into account our time effects, equal to 10.8. We can then find our short-term and long-term transform moment of inertia. And again, we'll use parallel axis theorem, and we'll assume that our moment of inertia of the pre-stressing and any steel itself is just equal to 0. So for steel and pre-stressing, we're only going to consider the AD squared component in the parallel axis theorem. All right, so our I transform short term is going to be our gross moment of inertia, 17,000 517 inches to the fourth, plus our AD squared component for our gross section, 352 square inches, times our D squared component, 10.6 minus 10.5 squared. And then we'll have our additional component from our pre-stressing. Sorry. We'll have 6.46 minus 1 times 0.651 square inches times our D squared component here, 10.6 minus 20 inches squared, which will give us a short-term transformed moment of inertia equal to 17,831 inches to the fourth. We can do the same thing then for our long-term, or with our long-term properties, and get an I transform long-term of 18,460. Next, we're going to find our decompression force and moment, and we'll use the two equations that we derived in class, our N naught and M naught, with the simplifications that we had in class as well. For our N naught, so our N naught sub S is going to be equal to E sub P effective 27,930 KSI times our locked-in pre-stressing 6.4 times 10 to the negative third times our area 0.651 square inches minus EC effective 1,577 KSI times our shrinkage strain, negative for compression, and so negative 3 times 10 to the negative fourth, times our gross area, 352 square inches. So this will give us an N naught S equal to 282.9 kips. Next, we can find our M sub naught S. So we'll get this value to equal 27,930 KSI times our locked-in pre-stressing strain 6.4 times 10 to the negative third times the area 0.651 times the distance between the centroid of our pre-stressing and the transformed long-term centroid of the section, 20 inches minus 10.8. And then we add in our effective modulus for our concrete, 1,577 KSI times negative 3 times 10 to the negative fourth times our gross area here, 352 square inches, times our distance between the top and the centroid of our transformed section minus the distance between the top and the centroid of our gross section. So here we'll have 10.8 minus 10.5 inches. So we'll get our M sub naught S equal to 1,020 kip inches here. Remember, because we're taking into account the effects of our pre-stressing and our long-term effects in our M naught sub S and N naught sub S, our live load N naught and M naught are going to both be equal to 0. So we don't want to count it in both places, so we're only including it in our M naught sub S and N naught sub S. And we'll use these values on the next couple slides to calculate our strains and stresses. We can now find the strain at the centroid and the curvature for both our sustained and live loads here. So starting with our sustained load, we have no applied axial load, so 0 minus 282.9 kips divided by our EC effective 1,577 KSI times our transformed area 362.9 square inches, which will give us a strain here of negative 4.94 times 10 to the negative fourth. We can do the same thing with our live load, and we'll find a strain at the centroid due to the live load of 3.19 times 10 to the negative fifth. So then we can come with our sustained load and find the curvature. So we have a sustained load here of 600 kip inches minus 1,020 kip inches divided by our effective modulus, 1,577 KSI, times our transform moment of inertia, 18,460 inches to the fourth, will give us a curvature here of negative 1.44 times 10 to the negative fifth radians per inch. And again, we can do the same thing for our live load, noting that we have no decompression load or decompression moment here for our live load components. We can then think conceptually about our strain at the centroid and our curvature. We can see that our applied moment is less than the moment caused by our pre-stressing. So we would expect a smaller compression in the top than in the bottom for our sustained loads. And with our live loads, we would expect tension in the bottom and compression in the top from our live loads. So these would be our strain diagrams and curvature for our sustained loads and our live loads here. Our next step is to use that strain at the centroid and curvature that we found on the previous slide to find the strain at the top and bottom of our section, the stress at the top and the bottom of our section, and the strain and the stress in our pre-stressing. So we'll start with the strain at the top of the section due to our sustained loads. So here we'll have our epsilon CT is equal to our strain at the centroid, which is negative 4.94 times 10 to the negative fourth, minus our curvature here, which is negative 1.44 times 10 to the negative fifth, times the distance between the centroid and the top of the section, 10.8 inches. So we'll get this strain here due to our sustained loads to be equal to negative 3.38 times 10 to the negative fourth. And we thought that we would be adding, or we would have a smaller compression at the top than the bottom, so we can compare this strain to the strain at the centroid and make sure that we're less here. So we are, so we know that we have our signs correct. So then to find the stress at this point at the top, we need to take our modulus, so 1,577 KSI, times our strain, negative 3.38 times 10 to the negative fourth, minus our shrinkage strain. So we're going to add in 0.3 times 10 to the negative third. And here we'll get our strain to be equal to negative 0.06 KSI. So we can do the same thing for our bottom strain. Note that the distance between the centroid and the bottom should be negative here. So we'll have a larger strain than at the centroid, which is what we would expect. So we find the strain at the bottom, and we can take that times the modulus after we take out the shrinkage strain. So we'll get a stress in the bottom fiber from the sustained loads equal to 0.61 KSI. And then we can do the same thing with our pre-stressing. So the strain at the centroid minus our curvature times the distance between the centroid and our pre-stressing. We have a negative distance here, 10.8 minus 20. And then here we need to add in that locked-in strain differential, delta epsilon p, to give us our final strain. And then we can get our stress just by taking our effective modulus for our pre-stressing, 27,930 KSI, times that strain that we found, 5.77 times 10 to the negative third in tension. And we'll get a strain here of, a stress of 161.2 KSI. We can see that this is less than the yield strength for our pre-stressing. So we know that all of our linear elastic assumptions are okay. Now we need to repeat the procedure that we followed on the previous slide, but we need to do it for all of our live loads. So we have our strain at the centroid of our section due to our live loads and the curvature, and we can use that to find the strain at the top and strain at the bottom of our section. We can take that times our modulus, so this is just our normal modulus, not the effective modulus this time, to get our stress at the top and stress at the bottom. And we can do the same thing for our pre-stressing. Note that with the pre-stressing, we already accounted for the effects of pre-stressing, so we already included that locked-in strain differential with our sustained load, so we don't need to include it here as well. So we can find that our live load is going to cause an additional 5.8 KSI in our pre-stressing strands. So here you can see the stress in the top fiber from the live load, negative 0.72 KSI. The stress in the bottom fiber of our concrete, 1.22 KSI tension, and the additional stress in our pre-stressing of 5.8 KSI. Our final step is to add together the stresses from our different components. So we add together our stresses from our sustained load with our stresses from our live loads. We can do that at the top of our section, and we'll see that we have stress in the top of our section of negative 0.78 KSI compression. And in the bottom, we have a stress of negative 0.61 plus 1.22 KSI. So we're going to have 0.61 KSI tension there. So we can compare this stress in the bottom to the tensile strength of our concrete, 7.5 times the square root of F prime C. And we can see that our tension stress is going to be greater than the tensile strength of the concrete. So because of this, we would expect our section to crack. So we would, if we wanted to prevent cracking, we would need to either increase the strength of our concrete or change our section shape, or we can add additional pre-stressing. We can do the same thing with our pre-stressing, adding the our stress in the pre-stressing from our sustained loads, the stress from our live loads to get a total stress in the pre-stressing of 167 KSI, which is less than our yield stress, so we know that we're still in the linear elastic range. So that concludes this example. You can also find stresses at release or transfer using a similar procedure where you would use the release concrete strength and the self weight.